I call this one the merry-go-round lesson. I think it's the easiest way to visualize what's going on here. So we're going to be using linear and angular speeds to describe motion on a circular path. Let's start this out by saying you're told by a PE teacher that you have to run 4 laps around the track. Which lane would you choose? I know this is an oval, and we're going to be dealing with circulars, but I think this is relevant. Okay, so if you're like me, I would choose number 1. Why would that be? Because that would be the least amount of running. You might be a cross-country runner, and you might like the challenge of going in 8, because that would be the longest path. But I, at my age, maybe if it was rollerblading, I would do 8. But if it's straight up running, I'm on 1 all the way. So why is that? Well, we know that that's a shorter path. And to help us illustrate this, this is a high school indoor track team. I got it from a New York newspaper. And look at all those kids. They know what's going on. They know what's up. They are all in the inside lane because they know that's the shortest path, and they're more likely to win the race if they are in that lane. So let's take a look at what linear speed is and what angular speed is, and how we can visualize it, how we can understand it. And that's where the merry-go-round comes in. So I'm going to draw a top-down picture of a merry-go-round right now. It's not going to be pretty because I don't draw pretty. I never did. All right, so that is the full merry-go-round, right? Here is a point on the outside, and then there's also horses and things like that on the inside, right? So there's also like a horse here going along another circular track that we can't see quite as easily. All right, now, here's the thing. If you and your friend sit in these seats, you guys are going to be right next to each other at the start, and you're going to be right next to each other at the end. But will you have traveled the same distance? No. No, the person that is in this seat right here will be traveling further distance. And then you can conclude a faster speed. The person on the inside is going to be going a much shorter distance, but they're going to end up in the same place. Okay, these horses are built, or they're bolted into the ground. So you're going to end up in the same positions, but you'll be going different linear speeds. Okay, so what does linear speed refer to? That refers to how fast an object travels on the edge of a circle, or on the circumference. And angular speed is how fast the object turns. And one of the key things that we'll see in word problems like this is revolutions. It'll say like revolutions per second or revolutions per minute. And in that case, you're being given the angular speed, and you have to find the linear speed. So let's investigate a problem with this. We're going to kick off with something really, really simple. This is not pre-calculus stuff. Let's just look at how we would measure speed. If it was just a regular linear, just a straight line. So Tom ran 432 feet in 6 minutes. What was his speed? Remember, we would solve that by taking the total distance, and we would divide that by the time. So distance divided by time. And that would give us our speed. And our speed is always measured in time per, distance per time units. So it'd be like miles per hour, or in this case, feet per minute. So this gives us the total distance. It says 432, and it's 6 minutes. So what we'd have to do to find that out, I think that's 72. Hold on, 72, okay. So we would say, okay, it's 72 feet per minute. So take a look at what we did again. We took the total distance, divided it by time, and that's how we got our speed. We're going to do the same thing right now, but it's going to be involving linear speed. So the planet Saturn has a radius of 36,000 miles, rotates 1 revolution every 11 hours. What is the linear speed of a point on its equator in miles per hour? So on its surface, this looks a little bit more intimidating than the Tom Brady problem, but it's really not. We just have to do one extra step here. So we're still going to do distance, right? Distance divided by time. Okay. And let's see here. What do we got? We got a radius of 36,000. So I'm going to draw that. Oh, it's not a very good drawing here. But this is the point and it's traveling. So let's figure out. 36,000 miles, 1 revolution every 11 miles. So this is key information right there. 1 revolution every 11 hours. And that gives us our time. So I'm just going to put that right here right now. Okay, so 11. I'm going to be dividing by 11. Now we got to find out the distance. Now some people might think, oh, 36,000, that's the distance. No, 36,000 is the radius. The 1 revolution all the way around, that's the circumference of a circle. Remember, that's going to be 2 pi r. Now they give us r, they tell us it's 36. So our distance traveled, to calculate that, we're going to do 2 times pi times 36,000. Okay, that's going to be 72,000 times pi. Oops. Still over 11. Let's get the calculator out for that one. So might as well just 72,000 times pi. That's okay. So that right there is the total distance traveled. 226,195 miles. So 195 miles. That's close enough. So that's the distance it travels all the way around the planet. Okay. Now that's going to be divided by the number of hours, which was 11. So now we've got this. I'll divide this by 11. Okay, so the speed, the linear speed of a point on its equator is 20,563 miles per hour. That's how fast a point on the surface of Saturn is rotating around the center of the planet. All right, so this problem is I've already got started on it here because they were trying to trick us. They're saying, oh, a flywheel with a diameter of 12 centimeters. Well, diameter, we're looking for radius. So I already did that just to prevent myself from making that mistake. It's rotating at a rate of 7 radians per second. And oh, that's nice that they gave us to us in radians. Unlike last time where they gave us feet. Giving us in radians is perfect because remember, a radian will be the same length as the radius. So it's going to be 6. We're just going to have to multiply by 6. What is the linear speed of a point on its rim in centimeters per minute? One thing I noticed here is it says in centimeters per minute, and they gave this to us in seconds. So we're not going to be dividing here. We're going to have to multiply. So just to visualize this, every radian is going to be 6, right? It's going to be the same length as that radius. So, 1 radian there is 6, 2 radians, 3 radians, 6. So this is going to be pretty simple. What we have to do first is multiply the radians per second to get to minutes. How many radians would that be in a minute? Well, 7 over 1 second would equal what over 1 minute? Well, that's a times 60, and then this would be times 60 as well. So that would be 420 radians per minute. So 420 radians per minute. Radians per minute. And how much is each radian? Well, each radian is going to be 6. Because the radius is 6 and the radian is equal to the radius. So we just have to do 420 times 6, and now we'll get our answer. And 6 represents the centimeters. That's going to be 2,520 centimeters per minute. All right, let's look at a slightly trickier one. On a carousel, the outer row of animals is 18 feet from the center. The inner row is 9 feet from the center. The carousel is rotating at 3 revolutions per minute. What is the difference in feet per minute in the linear speeds of the animals in the outer and inner rows? So, first thing I want to note here is so we've got 3 revolutions per minute. Okay, so we're going to be multiplying again because we're going to be finding out the smaller value, like 1 revolution per minute, and then multiplying by 3. So let's draw this thing out here. We've got, that's the entire carousel. This is the outer row, and that has a thing here of 18. Okay, so that's 18 feet from the center. And then there's an inner row, and that is 9 feet from the center. So I'm going to make a little table here to help us keep track of everything. So here I'm going to put the inner and outer rows, and then I'll do 1 revolution and 3 revolutions. Okay, so the radius for the inner is 9 feet, and for the outer it's 18 feet. Okay, so for 1 revolution, we're going to do 9 times pi times 2, or I should keep it with the actual formula here. Just 2 pi r, remember, is the circumference of a circle. So we do 2 times pi times 9, which would be 18 pi. Okay, now that's 1 revolution, 18 pi. So that means 3 revolutions would be 3 times that, which would be 54 times pi. Okay. Now, what about the outer? The outer would be, instead of 2 pi 9, 2 pi times 18, which would be 36 times pi in 1 revolution. 3 revolutions, we multiply that by 3, and that is 108. Now we've figured out in the foot per minute here, this is the feet that they travel per minute. The inner is 54 pi, the outer is 108 pi, and it wants to know the difference in feet per minute in the linear speed. So all we have to do is 108 minus 108 pi minus 54 pi, and that is 54 pi. And that's going to represent the difference, but let's turn that into a nearest foot per minute. So 54 times pi, 170. So that's about 170 feet per minute. The linear speed of the outer is about 170 feet per minute faster than the inner horse. So we've done a few examples here, and in each case what we've done is taken the arc length and divided it by time. And that's how we've discovered our linear speed. Now linear speed is often represented with a variable v, so you might see a shortcut to this formula, v equals s divided by t. Let's apply that to this problem so we can see how just putting in the formula will be very, very simple. Angular speed of a point on the planet is pi over 13 radians per hour. Okay, that's going to be very tiny. So pi, because if you think about it, 90 degrees is pi over 2. So pi over 13 radians, that's going to look like this. It's not going to be very, very large. So then you take the arc length of this, and we're going to divide it by the time that we are given. And it looks like pi 13 radian per hour is what we're looking for. Let's figure out that arc length. And remember from earlier lesson, we've got arc length equals the pi radians times your radius, right? So we have that. That's going to be pi over 13 times 5,000, which is going to give us an arc length of 5,000 pi over 13. All right, so that's going to be the arc length. Now let's go ahead and find out what that actually is. We got 5,000 times pi, and we're going to divide that by 13, and that's going to give us about 1208. Okay. About 1208 miles. Now, what is the hour? How are we going to figure that out? Well, it's given to us in radian per hour, and it wants to know miles per hour. So it's really, the time here is just 1, since we already have that. So our solution is going to be 1,208 miles per hour. Up till now, we've only dealt with linear speed, but remember, we're also going to be learning about angular speed. Angular speed, if you recall, is how fast something turns. And the formula we use to find that's very logical. We represent angular speed with that little w, and that's going to equal the angle theta divided by the time. So again, it's distance, or in this case, the angular movement or angular displacement divided by the time. Let's go check out one of these problems. So we've got a windmill, has a blade 30 feet long. Find the angular velocity, and it gives us the linear speed right here. All right, I prefer speed because velocity you should be saying the direction that it's going into, but you know, we'll just go velocity and pretend it's synonymous with speed. Anyway, 438 revolutions per minute. The windmill is has a radius of 30 feet long. Okay. All right. So let's concentrate on what revolutions per minute means. Revolutions, remember, is one full circle. And what is that? Hopefully you're saying, well, that's 2 pi. Okay, so what we're going to do to solve this is let's figure out how many revolutions, how many radians it travels in a minute. So we're going to do that by taking the 2 pi there, the distance or the circumference of a circle, and multiplying that by this 438.8. And that's going to be, I don't need a calculator for this one. All right, so that can be represented as 8,707.6 times pi. Okay, so that's our theta there. That's the distance in radians. So remember, I should have put the formula over here, but that over time. Okay, so what do we have here? That's saying we're going this distance, 877.6 times pi, over 1 minute. So in 1 minute, that's how far it's traveling. Okay. So we have the angular velocity in minutes, but they want it in seconds. So we want to know per second. So that's pretty simple, right? All we have to do is divide this 877.6 divided by times pi, and divide that by 60, just like you would divide a minute by 60 and get the number of seconds, which would be 1/60th. So let's go back here, 876.5. Don't forget times pi, and now we can divide this by 60. All right, so it's about 46 radians per second. So around 46, we'll say. Notice that the 30 feet for the radius did not play a function in this equation.